Welcome to This Explainer. Today, we're going to unpack something that sits at the absolute beating heart of data analysis. We are talking about regression statistics. Now, it's an incredibly powerful tool, right? We use it for everything from predicting global economic trends to analyzing life-saving medical trials. But here's the catch with regression. It is also incredibly easy to misunderstand. If you don't know the hidden rules operating under the hood, well, your entire analysis might be completely compromised.
So, let me ask you a rather blunt question. Is your seemingly perfect regression model actually lying to you? Think about it. You might have run your data, looked at your output, and totally celebrated a highly significant result. But if that model is secretly built on a cracked foundation of broken statistical rules, your results might literally be invalid. To really set the stakes for us here, take a look at this quote from econometrics expert Mike Jonas. He points out that, before we can do anything further in terms of extracting interpretation out of those coefficients, we need to make some assumptions. And you know what? He's absolutely right. We can't just trust the data blindly. We have to understand the mathematical rules of the game first. If we skip that step, our interpretations are really just guesswork disguised as math.
So here is our roadmap for today. First, the rules of regression. Second, myth-busting regression assumptions. Third, the measurement error trap. And finally, time series and autocorrelation.
Let's dive right into Section 1, the rules of regression.
Think of these rules as the absolute bedrock of any trustworthy analytical model. To anchor ourselves, let's just quickly define what we are actually doing when we run a standard regression. We're typically using a method called ordinary least squares, or OLS for short. OLS is essentially the mathematical engine that we're trying to optimize. We are optimizing the intercept and slope to minimize the total distance between our data points and the regression line. But for this engine to run smoothly, the environment has to be just right.
And that ideal environment, that's defined by the Gauss-Markov assumptions. These are your baseline conditions. We absolutely need linearity in our parameters. We need our error terms to average out to zero. We need those errors to be completely independent of one another. We need homoscedasticity, which just means the variance of our errors is constant. We need a normal distribution of our errors. And finally, no perfect multicollinearity, meaning our explanatory variables can't be perfect linear functions of each other. If this foundation is cracked even a little bit, our OLS model is no longer the best tool for the job. Our predictions just can't be trusted.
Which brings us to Section 2, myth-busting regression assumptions.
Now that we know the rules, I have a bit of a confession to make. Even highly experienced social science researchers frequently misunderstand these foundational rules and fall for a massive myth. The myth is that regression assumes your variables must have normal distributions. Seriously, if you search the internet for regression assumptions right now, you will see this everywhere, but it's entirely false. The fact is, the normality assumption only applies to your model's errors. It only applies to the residuals, that gap between your predicted value and the actual value. It does not apply to your raw predictor or response variables.
To really prove this, let's take a look at a simulated response variable y. Notice how it has two distinct peaks. It's heavily bimodal. It is incredibly far from a normal bell curve, and it's being driven by a simple dichotomous predictor with a massive effect size. And yet, when we run the regression and extract the residuals, they map beautifully to a straight diagonal line. This means the model's errors are perfectly normal. Even with a wildly non-normal response variable, the OLS assumptions hold up perfectly, and trustworthy inferences can still be made. All right, let's move on to Section 3, the measurement error trap. We're going to tackle a second major pitfall in regression analysis, and this one deals with how we handle imperfect data. To really grasp the scale of this misconception, consider this. An incredibly popular 2002 paper,
A paper that has racked up over 250,000 views and is highly cited in the academic community got a fundamental rule completely wrong. The authors claim that if you have unreliable measurement, meaning measurement error, it will always cause your simple regression coefficients to be underestimated. This is a concept known as attenuation. They even provided a classic formula to correct this supposed underestimation. But as researchers later proved, this assumes all measurement error is completely random and uncorrelated. And in the real world, that is often just not true. Think about it like this. If you're trying to measure hidden traits, say a specific cognitive ability, and a test score, situational variables like a noisy room or just general fatigue during testing can actually cause the measurement errors of your instruments to become correlated. They literally become linked together.
And when errors are linked, everything gets distorted. In the simulation we were just looking at, the true correlation between those two underlying latent variables was only 0.15. But because the measurement errors were correlated, the raw test scores showed a relationship of 0.21. Now here's where the trap springs. If a researcher blindly applied that famous 2002 correction formula to fix the measurement error, the formula would spit out a corrected correlation of 0.31. The researcher would walk away thinking they fixed the problem, but they actually wildly overestimated the true 0.15 correlation. The big takeaway here? You absolutely cannot just assume measurement error makes your findings more conservative. It can actually inflate them.
Finally, let's wrap up with Section 4, Time Series and Autocorrelation.
Let's see how all this builds into the real world when we examine time-based data, because this is where the crucial independence of errors rule is frequently broken. When we track data over time, like stock prices or maybe daily water temperatures, we run into something called autocorrelation. Autocorrelation is basically the degree of similarity between a given time series and a lagged or delayed version of itself over successive time intervals. In plain English, it means that a data point today is statistically dependent on the data point from yesterday. Remember those Gauss-Markov rules we covered in Section 1? One of them was that errors must be independent. Well, ordered time series data often violates this fundamental assumption because past values directly influence present values. So if you run a standard regression on autocorrelated data, your model might look like a fantastic fit, but it's highly likely it's just tricking you. Thankfully, though, there's a really practical tool to detect this. It's called the Durbin-Watson test. You basically run your regression, extract your errors, and plug them into this test. It's going to output a number between 0 and 4. A score of exactly 2, you're in the clear. There's no autocorrelation. A score between 0 and 2 indicates positive autocorrelation, meaning a positive error yesterday likely leads to a positive error today. And a score between 2 and 4 indicates negative autocorrelation. Knowing how to interpret this simple little scale allows you to instantly diagnose whether your time series residuals are breaking that golden independence rule.
Which brings us to our final thought for today. We've seen how a cracked foundation invalidates the whole house. We've seen how perfectly normal variables aren't required, but normal errors absolutely are. We've seen the danger of blindly correcting measurement error, and we've explored the hidden dependencies lurking inside time series data. All of this, the whole shebang, really comes down to what happens after you fit your model. So, I challenge you. How often do you actually check the residuals of your own regression models? Because I promise you, if you aren't thoroughly investigating the errors your model leaves behind, you might just be letting your data lie to you. Thanks for joining me on this explainer, and keep questioning the data.